Thanks for the introduction, Brett. Hello. And very interesting, humanitarian AI. Sounds interesting and really important. So anyhow, I'm Amy Hodler, Director of Graph and Analytics in AI Programs and Marketing at Neo4j. And I'm here with my colleague, Dr. Alicia M, a Director of Product Management for Graph Data Science. Last spring, if you remember, or if you're new, it feels like forever ago, but we launched Neo4j, the Graph Data Science Library, to give data scientists a framework for leveraging relationships and kind of structural information for analytics and machine learning. This year, we've added a lot of new capabilities and updates, so it seemed like a good time to give you guys a quick update. We'll do a level set, then we'll cover what we're enabling for more data science capabilities, offering InGraph machine learning, and providing a fast path to production for graph data science. So on this first slide, just to kind of give you a look at what we're doing and what we're seeing out there, we're actually seeing quite a bit of uptake, and we know graphs have been exploding in AI research. The chart on the upper right here shows kind of nearly exponential growth for AI research featuring graphs. But this isn't just academia. We're also seeing this explosion in the commercial world as well. So according to Gartner, graphs form the foundation of modern data and analytics. And I know you heard that earlier today if you were listening to the keynote. And part of that is because graphs enable data scientists to create very faithful representations of their data, build models that are more predictive, and make them more explainable. And so it's not surprising that Gartner has actually found that teams with higher AI maturity are more likely to use graph techniques. At the highest level of maturity, up to 48% of them using graphs. And because Neo4j is the graph data company, we're also seeing this enthusiasm for data science in the Neo4j community. We have a graph algorithms O'Reilly book with over 207 hundred thousands of downloads, 4 times growth with data science web pages, and just a really vibrant community applying graphs to analytics and data science problems. So if you think about it, we've got 3 trends here. We've got a really strong academic trend that started a few years ago. We've got a strong commercial application trend that's surging right now, and an increasing engaged community around data science. So why are these things coming together? And on the next slide, we can actually look at what is the foundational reasons of why this is coming together. So if we think about this, it really comes down to very simply the fact that relationships are actually the strongest predictions of behavior and complex outcomes. So there's been a lot of research using relationships to make predictions, and we saw that on the last slide. And what they found is that you can make better predictions by looking at people's friends and their friends' friends than you can about information about that original person. This book, for example, James Fowler's book, Connected, details a lot of research that shows how you can better predict. And in one example, better predict whether someone's plans to vote based on second-degree relationships. So if you think about what that means that people, your friends' friends, people you don't even know, are more predictive of your behavior than your simple demographic information like age, zip code, income level. And so those relationships are really strong signals, but you can't use them if you can't get at them, if you can't see them. And unfortunately, most analytics and data science kind of ignores relationships because they're so very hard to use at production scale in machine learning. And if you consider manually looking at voter or a voter, let's just take a voter, and looking at their behavior and their friends, a few hops out from them, from one person, okay, might be slow, might be tedious, but you can do it. Now think about trying to do that manually or even with tools over a complete graph for everyone, and then transforming those results into a flat format for machine learning. I mean, the complexity explodes and it becomes impossible very fast. But with graphs, graphs explicitly created for and by relationships for analysis. If you create a graph into a native graph format that's tuned to be very efficient at storing and computing and using those relationships, that becomes very effective and very efficient. So once you have your data in a graph, you don't have to guess at correlations because they're already inherent in the relationships. They're built in. And you can then infer meanings using things like graph algorithms to make predictions. And so on the next slide, we look at like, what is the typical progression here? And so if we think about getting started with graphs and data science together, we get asked a lot about that. There's this natural progression which starts very naturally with just getting your data into a knowledge graph. And so most teams start using knowledge graphs to answer specific questions. And this is where your domain experts come in. They can explore and search for specific patterns they know are predictive or they just want to investigate. And they can do it in a way that otherwise previously would be just too complicated in a relational database world to pull all that information together and then to have those relationships revealed. And so once you're able to ask questions of your knowledge graph, the really easy next step is to use graph algorithms. So at this point, you don't have to have labeled data or even specific questions in mind. This is really about letting the graph kind of speak for itself. And so here you can use unsupervised machine learning techniques, identify trends, associations, outliers, in your graph to understand what's important in your graph, where possibly similarities may be, and how things are maybe grouped together. And it kind of points you to where to investigate further. And then once you're there and you're using graph algorithms, you'll probably want to build on that and do more sophisticated graph native machine learning. So at this stage, you'll want to have labels in your data. And that could be, let's say you have a graph with customers who buy products and you know who bought what, when, what the price was. You have all this information about it. Or perhaps you have a financial transaction graph and you have identified and labeled some possible transactions as fraudulent. So you have data, you have some labels there. And this is where you'd want to use graph embeddings to learn which features, what elements of your graph are important, what are predictive. And these are things that you don't even know to look for yet, which is kind of the magic of graph embeddings. And so you would be able to transform your graph and parts of your graph into a format for machine learning. And that's when you can take the more advanced training of supervised machine models to predict those labels on new incoming data. So remember, you had data, it had some labels, you've done a model, and you might want to do something like predict who is going to buy this particular product next, or what kind of product they might want to buy, or who's a fraudster. So you had some labels, you did your model, now you had new data in, it's like fraudster or not. And so it's pretty simple evolution if you think about it. It all starts with getting your data into a knowledge graph to look for patterns that you know you want to find. Then using graph algorithms to help you find what's important without labels. And then once you have labels, maybe you've run some algorithms, you've done some features, you can then train embeddings and use supervised machine learning models to predict how your graph will evolve over time. On the next slide, we look at what Neo4j has to offer for you. And so looking at and working with customers and users and community users, we realized we needed to develop a package, really. And this is where, to enable this process, this is where the graph data science framework comes into play. So at the center is the Neo4j database. You've got to get your graph from somewhere, you've got to store it somewhere, and to do it in a native format for super fast queries and graph persistence is kind of the way to start. And then we have the GDS library, the Graph Data Science Library, which includes an extremely scalable analytics workspace to do analytic stuff, graph algorithms to look at understanding and finding your patterns, and then InGraph machine learning as well. And the GDS library also automatically transform your graph from the database to this analytics workspace for whatever shape you might need for your problem. And Alicia will talk a little more about that later. And then finally, we've got Neo4j Bloom Visualization, which is a product for obviously visualization, but exploration, collaboration, looking at the results once you have them, and prototyping as well. And so on the next slide, we'll kind of just sum up things. So if I had to sum it up from here, why do people use graphs in analytics and machine learning? It's really just simply because they can make better predictions with the data they already have. And we hear a lot from data scientists that, boy, if I just had more data, I can improve my predictions. But that's often not as easy as it sounds. Either it's not feasible to get more data, or you get more of the exact same type of data that you had, and that doesn't really get you the improvements that you're looking for. So by adding in relationships and network structures that's already kind of hiding in your data, you kind of get to double dip. You get that. You get to add more information that was previously tossed out and not used. And then you get to also diversify the type of information you're using in your machine learning data as well. So adding graphs to existing analytics and machine learning pipelines helps you uncover those patterns you'd like to see, increase predictive accuracy, and perform more context-based learning. So with that, I'd like to turn it over to Alicia to talk about what's new this year.
Thanks. So now that we've kind of level set with like, what's all this about, we're going to kind of shift gears to talk about what's changed in the last year and kind of more focused on the last couple releases of GDS. And kind of one of the main themes is making it easier for you to do data science and get up and running quickly, show value with less friction. So you should not need a PhD in network science and graph algorithms to get some insight out of your connected data. You shouldn't have to be a database administrator to do graph data science. We've really focused on making this process easier for everyone so you can get started quickly. And so you might have seen this in the keynote. I like to kind of level set and contextualize, when we talk about graph data science, we're really talking about machine learning. And you can divide that into unsupervised machine learning, where you're really just kind of letting the data speak for itself. You're finding patterns, trends, anomalies, but you don't have labels. It's just, I've got a lot of data. How do I make sense of it? On the other hand, we talk about supervised machine learning, where you're making predictions based on labels. And Neo4j kind of does both. So when we talk about unsupervised machine learning in graphs, that's really your classic graph algorithms, right? Clustering is community detection. Association is similarity and pathfinding. Or dimensionality reduction is centrality, what's most important, or the graph embeddings. And then we talk about supervised machine learning. In Neo4j, it's possible to do link prediction and node classification. But for this section, I kind of want to start by focusing on graph algorithms. And so this is where we started. We've got our 6 categories of algorithms, pathfinding, so you can find the shortest path between 2 nodes or check what paths are available. We've got centrality and importance, which is your typical clustering. So if you've ever done, KNN or K nearest neighbors on your tabular data, you can do Louvain or, centrality and importance is your which nodes are important. So think about things like PageRank, which nodes are most influential, or you can do something like degree centrality, which is how many connections do your nodes have. These basically tell you what's most important in this big data set. So I already talked a little bit about community detection, but this is clustering your graph. So KNN on your tabular data, Louvain or label propagation on your graph. We have heuristic link prediction, which gives you a pair of nodes, and there are some rules like how many common neighbors do they have? This is the likelihood they should be connected. We talk about similarity, which is here is a pair of nodes. How similar are they based on their relationships, their neighbors, their properties? And then the graph embeddings are your kind of super algorithm that can kind of translate everything important about your graph into a machine readable format for predictions. And this is really kind of the unsupervised side of the house. We talk about focusing on this because we offer more in-database graph algorithms than any other vendor. So we try to cover the bases of how do you make sense of your data. One thing we've been focused on in the last year is adding the algorithms you've asked for. So in the centrality space, we added HITS, which is hyperlink-induced topic search. It's basically 2 different types of centrality measures in one. And influence maximization, which I'll talk a little bit more later. In community detection, we added speaker-listener label propagation, which is really a multi-label community detection algorithm. So it lets you find overlapping communities in your data set. And then similarity, when we introduced all the graph embeddings in, I think, our 1.4 release, we talked about this at Nodes last year, we added K nearest neighbors right after that to make it possible to make use of your graph embeddings really quickly. So it takes your tabular data and builds a nearest neighbors graph from there. That's not enough, though. We don't just kind of introduce an algorithm and stop. We focus on making the existing algorithms better. So in the pathfinding and search space, we've standardized the API in our last release. So all of the pathfinding algorithms in the product tier have the same API. You call them in the same way, and they return the same things, making it easier. For the centrality and importance algorithms, in our 1.6 release, we moved a bunch of them to the product tier, and that's that fully supported, scalable robust space where we really have spent time re-implementing them and making sure they scale for you. So we moved degree centrality, article rank, eigenvector centrality, all of those have moved up to the product tier. In community detection, we recently introduced the ability to filter your write back for communities based on the number of community members. So you can say, I don't want to write back any community IDs that only have one member, saving you time and making it faster to get value. And then for the graph embeddings, we've been focusing on increasing the accuracy of them. So GraphSage is more predictive and making it possible to get consistent graph embeddings. So introducing seeding so that you can seed your random number generator, generate the same random walks every time you run Node2Vec, and get the same results back again. But that's great. The problem is they need to be fast enough to run on your data. So we spend time optimizing these as well. We talked about this in the keynote, but Dijkstra got 25% faster. Actually, all of the pathfinding algorithms moved up to the product tier have been optimized for performance. In our last release, PageRank got almost 90% faster. Faster means you can run it on bigger data sets. And Node2Vec, which is funny because when we introduced this, I was like, it's a slow algorithm. There's nothing we can do about it. The engineering team surprised me as always, and it's actually 60% faster due to some new optimizations. So we continue to improve these. Just to spend a little time on influence maximization, because it's new, it's a totally new centrality algorithm for us. What this is it's a way of figuring out which nodes in your graph are most influential. And you can think about it in like real world terms, as in, I have a limited budget. I've got a social network. I want to know who I should market to drive the most adoption, to make my product go viral. Or if I'm trying to figure out which blog or news site to read first, and I've got news sites that cite each other, I want to figure out which 3 are the most influential in that network. That's influence maximization. Or to kind of make it more real in the context of the last year of all of our lives, you see influence maximization used in epidemiology when you want to look for early warnings of an outbreak. So if you have a limited budget, you can only test a certain number of people. You can use influence maximization to figure out who are the super spreaders in your graph and where should you intervene. So these are really powerful algorithms. If you want to think about them in mathematical terms, it's kind of given a network with n nodes, and you need to find a set of k nodes to spread to most of the graph. It's basically a set cover problem. And so what we've introduced are 2 different methods, basically approximations. So this is combinatorial optimization, super computationally complex. There are 2 different methods of approximating this, the greedy method and the CELF method. And CELF is a more recent method. It's faster on big graphs. But what's really exciting here, and we wanted to highlight for nodes, is these were actually contributed by a community member. So not by someone on Neo4j's engineering team, but one of our lovely community members who'd been using the library, getting value out of it, and was able to implement these algorithms using our internal APIs, opened a pull request, and we were able to include it in the library. And for us, this is really just validation that we've built something, we've built infrastructure that others can use and find value in. And so we're really excited to talk about this today. And so now I'm going to pass it back to Amy to talk about InGraph machine learning.
Thanks, Alicia. I think the gauntlet's been thrown down. We need the community to add more graph algorithms. Who's going to do the next one, and what's that going to look like? That's kind of a fun. We should do that every year at Nodes. Have a community contribution to share. So anyhow, back to InGraph machine learning. This year we also added InGraph machine learning, so inside of Neo4j. It's really exciting because for the first time, organizations actually can do a full machine learning lifecycle inside of a graph. And the next slide kind of goes back to something that you saw earlier, Alicia showed earlier. And to bring that lifecycle inside of Neo4j, we had to add supervised machine learning. And the graph algorithms, of course, we're letting those graphs speak for themselves and find those patterns. It's very data driven. And this is where the graph algorithms had focused on in the past, but now that we've added in a supervised machine learning, we're able to look at those labeled data to predict either number, a value or classification, and it's very task driven. So you have a specific thing you're trying to do. The next slide is another way to look at this and to think about it. So if we think about it, and I always think about it by what am I trying to accomplish? And so graph features and graph algorithms or queries to create features are used to make predictions based on or influenced by the structure of the graph. We know there's a certain pattern that's predictive or a value that's predictive, and we can use feature engineering to mine those and use those patterns. Now, graph machine learning models, they're on the right, are used to make predictions about the very structure of the graph itself. Now, this is where we want to predict how the graph itself will evolve in the future or should look different, like maybe we're predicting missing data, for instance. And if we do a double click on that, so the next slide, we look at what do we actually have. And if we think about supervised machine learning, of course, you're starting with that labeled data. In a graph, you have nodes that are either linked or not. That's labeled data. And then we also have features as well. And so you might have pre-existing attributes that maybe aren't necessarily predictive, or graphy, like your product node might have price, a number of items in stock, something like that. But then you maybe have also enhanced your graph with features by running those graph algorithms like the page rank to find the most influential product items and groupings, or embeddings to represent kind of a node neighborhood. And so based on that data, those labels, those features, we can use supervised machine learning in Neo4j to learn a function to make a prediction on new data or data we haven't seen yet. And there's two types of supervised machine learning in Neo4j. We've got node classification. What label should this node have? Should I label this new node like a fraudster or not? Link prediction, should there be a relationship between these two nodes? And will this person likely buy this product? So those are the two types. And the next slide looks at how they go together in a flow. So just a bit ago, we compared the features, the graph features and the graph models, if you remember. These type of graph-based machine learning techniques are used at different stages in the machine learning workflow. So we can see here in the first step, there's a graph native feature engineering, and then in the second step, we're training the predictive models. Now, training the graph models can be tricky, training graph models in general. There's a potential for data leakage, and it's just something that we've helped automate some of these steps, like some of the test train splits, the model scoring and the model selection to kind of help you through that process. And then from there, you'd want to use your models to actually make your predictions, and then either update your original graph so you can enhance your graph again and keep iterating on that. Or maybe you want to use them somewhere else. Maybe you want to export them into another system and do some other processing on them. And of course, especially for enterprise teams, you'll likely want to store and publish and collaborate on different models to compare results and work on projects. Now, previously, outside of Neo4j, data scientists would typically have a lot of tedious, and I would say, especially for someone like me, error-prone back and forth iterations to complete this kind of workflow. They'd go in and out of different products. So bringing this kind of workflow together in one platform has previously only been available with in-house tools at very large tech companies like Google and Facebook. But now inside of Neo4j, we are the first ones to have both unsupervised and supervised machine learning for graph together, and be able to enhance your original graph all without leaving the Neo4j environment. And so still being able to take those results outside, of course, but being able to do that in a much more efficient way. And the next slide, the other thing for the non-enterprise users that we're really excited for community users, for all of you here today, to say the Community Edition now supports 3 trained machine learning models. Alicia mentioned that earlier in the keynote. Previously, a community user was limited to just one model in the catalog at a time. And that meant you could train and use your models for predictions, but you couldn't easily compare different results and chain them together. And so we're just excited to open things up to community users and want to see more of the experimentation that the community loves to do. So I'll hand it back to Alicia to talk a little more about some other updates.
So all of this is great, but at the end of the day, with data science, it only matters if you can get something into production, if you can run something consistently, put it into production, deploy it on enterprise scale data. So the third piece of the puzzle, so we talked about reducing friction, making it easy to run algorithms. We talked about in-graph machine learning. The third path of the puzzle is really supporting your path to taking an experiment, a proof of concept, and kind of finishing that, deploying it, putting it in production. So when we talk about that, really it's kind of three pieces. One is repeatable processes. You run the same algorithm twice on the same data, you better get the same results or something's wrong. You want to be able to chain things together, build pipelines and workflows. You need to have kind of a production ready library, right? Able to handle big data sets, reshape your data, and have read replicas so you can scale out your queries. And then you also need kind of MLOps support. So you trained a model that's not useful unless you can deploy it, or you can kind of manage that deployment in Neo4j. So starting with kind of training models, we were really excited, I think 2 releases ago, to introduce the concept of the machine learning model catalog. So Neo4j is a database. We're good at storing things. Now you can also store your predictive models, your trained machine learning models for graph stage, link prediction, and node classification. Once you store these models in the model catalog, you can version them. They come with information about when they were trained, the schema, the type of model, and that lets you compare multiple models, run them side by side. In our enterprise edition, you can persist them. So you spent 3 days training graph stage, you can persist it. So if you restart your database, it's still there. You can also publish those models. So I made a really good model. I'm excited about it. I can publish it so I can share it with Amy, and anyone using the database can use it. And then kind of closing the loop, we added admin functions. So if I'm creating a bunch of models, Amy is creating a bunch of models, it's useful to have an admin be able to come in and remove models, publish models, make models private again, kind of control the data. So this is really about making it easier for, I've built my POC, now I want to share it with my team. I want to make it reusable. I want to deploy it. Another part of kind of making your production path easy is being able to get repeatable, consistent results. So you can create recipes with reusable components. You have your in-memory graph. You can chain multiple algorithms together, models, predictions. So you can kind of get value by, let's say you start with, I'm going to run Louvain. Then I'm going to use graph subgraph to separate out each Louvain community. Then I want to run node similarity on each of those communities. And then I want to use some of those communities as an input to my link prediction model. I've trained my link prediction model. Now I want to add some new results back to that graph. So I can kind of chain things together to get these usable pipelines. And then finally, you can reproduce your results with things like seeding. So if I've run community detection once, I can use those community detection labels, load those into memory, and then I can have the same community IDs the second time I run it. We also added random number seeding. So Node2Vec, FastRP, GraphSage, they're stochastic. If you seed your random number generator, you'll get the same results again, basically guaranteeing reproducibility. We also added things like scalars. So a really common practice in data science and analytics is you want to standardize, scale your data. So you can now use our scale properties procedure to transform your data on the in-memory graph. So maybe you ran PageRank, you ran betweenness centrality. PageRank is 0 to 4. Betweenness is 0 to 27. You want to compare apples to apples. You can use an L1 scalar so that there's 0 to 1, and you can compare them. Or if you're doing machine learning, a lot of those expect normally distributed data. So you can log transform your properties so they're easier and more predictive in your models. And what you do here is you just specify the properties you want to transform, and we return an array of those scaled properties. And what's easier here is you're not writing back to the database and doing it in Cypher. You're doing this all in the in-memory graph where it's highly parallelized. And this really kind of gets towards production-ready scale for big graphs. So you heard Meredith in the keynote. We're talking about users with billions of nodes. We introduced an enterprise-only compression format that uses 75% less memory. And so what that means is you can either run on a smaller box if you have less data, or you can run on more data on your big box. So you can get that full graph into memory. And you can use our native projections to load big data sets quickly. And sometimes folks say like, oh, but the native projections, I like Cypher projections. They let me reshape my graph. We've added features recently like collapse path to change your multi-partite heterogeneous graph into a monopartite graph using basically breadth first search behind the scenes. But it's super fast, highly parallel, orders of magnitude faster than a Cypher projection. And it lets you connect those people-to-people nodes based on a common item. You can also use our subgraph projections to filter your graph based on properties and create multiple in-memory graphs. So I run Louvain, and then I can create a whole bunch of subgraphs, one for each Louvain community. Final thing we want to touch on, and this was mentioned in the keynote, it's an important part of the 4.3 release, which you'll hear more about, is you can now have a read replica for your GDS instance. So Neo4j graph data science library built to run on a single instance. Your analytics instances or your GDS instance can now have read replicas, and those can serve as analytics instances for you to run read-only queries on for reporting without interrupting the algorithms. They can serve as visualization servers for you to run Bloom on, or you can have a warm backup for disaster recovery. So this is really about making sure your database is resilient for your production use case. And with that, finished 30 seconds over. I'm going to point you all at some resources, and then also check out our link prediction deep drive, which is in the data science track in about an hour or so. So check it out, and thank you so much.